So I come from the rocky aspect of solar system formation. So I look at meteorites and early Earth and things like that, and try and come from formation of the solar system from the other direction. And as Mike has so eloquently indicated, we start off with a molecular cloud. We end up with planetary system. We end up with objects in the early solar system. And seeing it's an astrobiology conference, I've got cat nerves, cats and rabbits. It could be a lizard. Yes. So that's my sister's cat. So the whole thing is that we need to be a bit more explicit here in step 2. And so Mike showed you what the difficulties are about going that way, taking the physics down. And from this direction, it gets complicated as well. And so the whole issue in terms of planetary systems is to try and reconcile the two fields. So what I'm going to tell you is a bit of a story. I like the story. It's a good story. It's evolving as time goes on. But it's sort of one aspect of trying to link up these fields, which I think is quite important. Now, we've also heard that photons are good, dust is bad, complete rubbish. Everybody in this room is here because of dust. Everything in this room is the dust, which is the debris of nucleus and so forth. And so the whole point is how do we go from that pretty pile of dust into something which is a fairly well-ordered planetary system, and in fact enables biology to take place and workshops and conferences like this to take place. So if we look at what we have in terms of our own solar system. So this is the only solar system that we can observe close up, and it's also a planetary system. So whenever you start thinking of exoplanetary systems, don't forget that we actually live in a planetary system, and everything that is in our own solar system is relevant to that discussion. So when we look at what's happened, we know that roughly 99.9% of the mass took off into the sun, 90% of the annular momentum stays in the planets, and reconciling those two things is a major feat as well. But if we look at our own solar system, what do we get from that? Well, we immediately see one of the difficulties of using meteorites to actually establish what went on. The age of our solar system is like 45, 67.3 plus or minus 0.3 billion years old. That's the refractory conclusions that Euro talked about. And some of the younger planetary events taking place at about 4.558 billion years. And then you get a residual tail relating to collisions and various other things. But most of the activity takes place in 10 billion years, 4.5 billion years ago. So that's the big issue for meteoritics. We get samples, we have no idea what the context is. Absolutely none. But we do have samples in hand, but museum curators are rather protective of meteorites, and so we might be getting something which is maybe a few grams, 100 grams if we're really lucky, to actually observe. And because we've got such small amounts of material, we've developed instruments to look at things in very close scales. We start looking at scales of microns, maybe down to meters. We also have a view of our current planetary system. We can see out Pluto now, nice images of Pluto. And this is completely at odds with the astrophysical perspective. So you're looking at star-forming regions. As Michael said, this is the ALMA images, and we're looking at our whole solar system and that in the region. We're not looking at Jupiter forming out in this sort of dark region here or anything like that. We're actually looking at our whole solar system being in that central blob. And so that's a big issue in terms of reconciling meteoritics, where you're looking at very small scales, with astrophysics or modeling, where you're looking at rather gross scales. So the key point for most meteoritists looking at the early solar system is that the further back you go in time, the hotter the solar nebula appears. And so here's a nice big CAI. This is about 50 millimeters across. This is really quite large. This is composed of high temperature minerals like spinel, titanium-rich pyroxene, malachite, anorthite, hibonite, it's a calcium hexaluminate. These are all fairly refractory sort of objects. This blue thing here is a hibonite. So this is the calcium hexaluminate. This one I did my PhD on quite a long time ago these days. But these are all very, calcium and aluminium are the major elements that will condense out of a gas of solid composition. And then you look at further into the ordinary chondrites, we see these round things in here, which are chondrules. And these are magnesium silicates, phosphorite. There's also iron nickel metal in there, so it's still composed of high temperature minerals. As I said, condensing gas of solid composition. So if we look at CAIs, and we start with the gas up here, and this is a sort of an equilibrium condensation model. So you put a gas up here, get it up to elevation, and bring it down. First thing you see is corundum, which is the aluminium oxide, then perovskite, which is calcium titanate. You get all these nice refractory minerals, galenite, which is the malachite, and then spinel, iron metal. All of these things that we're looking at in these CAIs look as though they've been a sort of a condensate from an equilibrium gas. And so when we look at the solar system, it's all put into context of melting, condensation, evaporation. We see minor isotope fractionations of magnesium and silicon. There's big oxygen isotope effects, but I'm mainly concerned about kinetic fractionation, which basically suggests evaporation going on in this one. We'll get back to the other one later. So geochemists love using rare earth elements, and there's a view from the chemists that we have to actually call these lanthanoids now. The lanthanides, they didn't trust us. They thought we might get confused with having a calcium lanthanide, a molecule like that, and so they wanted lanthanoids. So we just call them rare earth elements.
You can follow the astronomers and call them elements.
I did leave out my geochemist astrophysicist periodic table, which is a simplification. So if we start looking at the rare earth elements, and this one in particular, so let's start up here at the top right. This is a terrestrial basalts, nice smooth fractionations because the lanthanides are filling up the inner shells and they're basically increasing with mass, but they're not changing chemistry because the outer shells stay constant. And so effectively we get a different ionic radius, and that goes into different minerals in different ways. We get these nice smooth patterns, very nice. When we start looking at meteorites, we see something a little bit different. We have these group 3 patterns, which have depletions in europium and terbium. Now, europium can do strange things because it behaves as, when it goes to uranium 2+, it behaves like calcium 2+, so it can actually do some weird things with that. But the fact that you've got a terbium anomaly here is a characteristic of evaporation or partial condensation. These are volatility effects. They're depleted because it either evaporated the europium and the terbium away, or it condensed out of that gas and you got separated away from the solids, got separated away from the gas before the europium and the terbium came in. So nobody's quite sure what the direction was for these guys.
And you have to right. Why is it the case that lanthanum has like almost 2 orders of magnitude variability and non-number?
Depends on the minerals it's fractionating with. So that light rare earth element depletion will be, if you took away a pre-existing melt from that, will take away more of the light rare earth elements. So there's all sorts of fractionations going on.
A larger variety of holes. Lanthanum can fit into a large variety of holes than tungsten or whatever that is.
That's, yes. Let's move on. We're not talking terrestrial geochemistry today. So this is basically a signature pattern for condensation, because this is the group 2 pattern. It's got normal light rare earth elements, normal thulium, and then it's got depletions in europium and the terbium's down about there. And then these other guys, the heavier earth elements, are all depleted as well. And that doesn't make a lot of sense in terms of what's going on until you actually reorder the full element suite in terms of condensation temperature. And here we see that the middle rare earth, the light rare earths are up in this middle sector here, which is not depleted. The volatiles have all been depleted like those group 3 inclusions, but we're missing a great whack of material here, which is ultra-refractory. So you've had some sort of fractional condensation, you've had removal of this, it's gone off somewhere else, then the gases continue condensing and gets isolated somewhere else on another side. So this is clearly an indication of fractional condensation. but understanding what's going on is sort of rather difficult. So when you look at this, it sort of suggests that the solar nebula has to be hot. You have refractory elements in the gas phase, you've got fractional condensation, lots of homogenization of the original isotopic anomalies coming from the synthetic sites. And you've got all sorts of models in accord with thermodynamics. And that immediately raises alarm bells, because nature does not like thermodynamic equilibrium. We are not here because of thermodynamic equilibrium. Something's happened to fractionate all those elements and drive them apart. You've got to have isolated reservoirs, you've got to separate them. It's a dynamic environment. So even from the times of my PhD, it's like, what's going on? How do you get this separation in a hot gas? Something stays refractory, something stays in the gas phase at 3,000 Kelvin or 1,800 Kelvin or whatever it was. And then you've got to basically physically remove them. They've got to be separated. So there's a big problem in doing that. How big a region? How much of the solar nebula is up to that temperature? And there's all sorts of hand-wavy arguments about reservoirs and so forth. Is it a static cloud? Is it actually that much in equilibrium? And a lot of these temperature constraints are really tight. So the whole condensation of those heavier earths is taking place over 10 Kelvin. And so how do you get into a regime where you get such constant temperatures, but still getting isolation of those reservoirs and materials? The problem in all this is that all of these refractory inclusions are stuck in a matrix, which is basically remained largely cold. So it's all glued together in this fine-grained assemblage. There's this stuff called keratin, which is very similar to black stuff out on the road out there. It behaves like it chemically. So there's all sorts of different temperatures represented in these meteorites. So is this different place or different times or combinations? We just don't know. It's so long ago, and we don't have the temporal resolution. So depending on who you ask in terms of meteorites, what's the solar nebula? You'll get some answer like, it's hot. It's got to be hot. So you've got high temperature processing and meteoritic inclusions. There's no way around that. We've got to get very high temperatures sorted out. If you start talking to people who deal with matrices and so forth, well, it becomes a bit more complicated. So you get preservation of cold components as well as isotopic anomalies. Some of these nucleosynthetic anomalies do exist. So the big problem is that we've got this largely static view of the solar nebula from meteoritics. We know we need something hot somewhere. We just don't know where. Is this a radial effect of the solar nebula, or is it basically isolated pockets? And it's very difficult to nut out by just looking at the meteoritic stuff alone. Astrophysics isn't that much better, mind you. Well, it depends. So if the solar system forms out of a collapsing cloud of dust and gas, there's a lot of gravitational energy converted to heat. So there's plenty of heat available to actually look and see what's going on. We've got a nice incandescent sun. Star formations, of course, are cold on average. In fact, think about it in terms of the average density of the universe. It's pretty low, and it's sort of, we're looking at remarkable sort of processes going on. But I think that the key thing about the astrophysical modeling is that it's clear that we have to have dynamic disks. So we're getting the material spiraling in the form of the sun. We're getting the first dump, then spiraling. We have all sorts of issues of conservation of angular momentum. The dust will fight to stay in those Keplerian orbits. That, of course, is great because it leads to planets. We like planets, so we need to have that. But to accrete the sun, the dust has to not have a large fraction of angular momentum. And to get rid of that angular momentum actually requires energy. And so this is what sort of Michael was alluding to towards the end. There's an increasing recognition of transportation of material and angular momentum by jets and winds. So that's the context I'm going to try and put the observations of the solar system into. So there's a clear observation that most, if not all, young stars generate bipolar jets. And so this is an edge-on, these are images of an edge-on disk. in this region here, so we're just looking at them vertically away in both directions of these bipolar jets. That's a 200 AU scale bar. So it's a large scale object. And even in sort of a my broad sense, that jet itself is something like 50 AU across. And so maybe it's a bit less than that, a bit fuzzing, redistribution and so forth. Maybe it's 10 AU, maybe it's 20 AU. We just don't know. What would be really interesting to do is to find out how big a region that jet actually comes from. But you can see on this, these images here have been combined into the animated GIF on the right here. There's a big clump of stuff which starts going up. And so these jets are associated with accretion. So materials accreting onto this, from the disk towards the star, and then it's getting entrained in some sort of jet wind acceleration mechanism to be entrailed up. So some big clump of material came in, and now that's being pushed up in that jet. So the real question for me is, are those jets stellar, or right from the bipolar jet from the star, or are they associated with this?
Why are the jets only coming out in one direction?
They're not. Oh, because it's just to make it clear. Because they're trying to get the full extent. They actually do go down.
Sorry. It's also, it's a little tilted.
Yeah,
so a little bit towards perspective. So one side's coming towards us, the other's going towards you.
This is the photogenic side.
Not exactly. That's cool.
That didn't work. All right, so there's a increasingly, I think there's a role for a magnetocentrifugal acceleration going on to accelerate these jets. In winds, the magnetic field, like Michael said, the magnetic field lines thread through this weakly ionized disk. Protons get accelerated, protons being the ionized gas, and basically these can either entrain more gas, they can impact into dust and cause heating. So the astrophysical benefits of doing it through these magnetically accelerated jets is that this is a really energy efficient mechanism to actually do this. If you try to do it by thermal or photoevaporation, the amount of energy that's required is extreme, and it just can't drive things quite as forcefully as you would probably like them. And of course, the corollary to all this, which is alluded to many times even in astrophysics, is that nature's ability to generate magnetic fields is only matched by a willingness to ignore them. And so the magnetic fields are actually going to play an important role, I suspect, in doing what we need to get done. So how do we put the jet into a context of refractory inclusion formation? So where do the refractory inclusions form? Well, most likely close to the sun. That's a really useful sort of descriptor. Am I talking AUs? Am I talking 0.01 AU or whatever? But then if we do that close to the sun, that's the best heat source for doing this. Then use the jets and winds to throw this stuff back out into the outer solar system. And we've already seen what's going on in terms of the Stardust mission. So Stardust was a mission, flyby, it actually flew through the tail of Comet Dill 2, January 4th, 2004, and collected particles in aerogel, which is basically a polymer, which basically, if they dropped it, it just basically float down. So it's only sort of milligrams per large amount. And so this is basically a medium where you can decelerate particles. So the particle comes in. This is one here. It's been rich in ice and it's exploded as it went into the medium. And then you can pick up, there's a dark spot here, there's a dark spot here. You can pick up fragments of these particles. Now, when I first started to get involved with Stardust, it's like, well, what do we expect to find? Well, we expect to find things which are going to be submicron in comets that far out. Don't really want to get involved with that. Big mistake. Should have got involved because it turns out there are 30 micron inclusions in the Stardust residue, or Stardust wafers, might be a better term. And these are basically the solar system material. So that's actually a chondral olivine grain fragment. Now, who showed the picture of Genesis yesterday? We were talking about
Chris Mayer.
Chris showed it. So stardust operated with exactly the same return mechanism. So the idea is that you're coming in, whack, hit the top of the atmosphere, and you're coming in 11 kilometers per second. So it's like hitting a brick wall when you hit the atmosphere. There's no two ways about it. And that bump when it hits the top of the atmosphere is meant to start a accelerometer, start the countdown for when you release the drogue chute and release the parachute. So Stardust flew first. Took off, I guess 2005 return. Anyway, they both had the same mechanism. So Stardust was going to land in the Utah Salt Lake. Genesis was meant to come down on its parachute, get picked up by a helicopter coming along with a scissor, and basically pick up the drogue chute and then take it back and keep it nice and clean because you're trying to measure sort of minimum number of atoms of solar wind. And so when Stardust was coming back, everybody was very concerned that it wasn't going to behave the same way as it was going to behave the same way as Genesis would smack into the Salt Lake. And then it would be far more important because you've got very small particles. You really can't afford to have Utah Salt Lake splashed all through your aerogel. Turns out that the accelerometers were put in the right way around on Stardust, but on Genesis, they were put in the wrong way around. Worse than that, they had redundant accelerometers, so they were clearly worried that one of these things would fail, but they allowed the design allowed it to be put in the wrong way around. And so when it hit the top of the atmosphere, there was no change in state, and so it didn't go off into the Utah Salt Lake. But we digress. So that was a little interlude. So we know that refractory grains are present in the comet-forming region, and for all intents and purposes, there's also refractory inclusion material out there. So there's nothing pure in the solar system. You've got to get inner solar system material out to the outer solar system. So jets and winds are clearly in vogue in terms of how we see our solar system operating. But we've still got issues remaining about if we try and get too close to the sun and form things down there, how do you get it out of that gravity well and get large things, not just gas and very fine dust, but actually large particles out to the outer solar system? And so this was where the X-wind models came from about 1996. And so if you're forming a bipolar jets close to the sun in this region here, then there's a crossover in the magnetic field lines just in here, where you can accelerate material to the outer solar system. But there's all sorts of issues. I'm not going to go into them. Everybody's sort of fallen out of favor a bit with the X-wind models. You get all sorts of uncontrolled mixing of matrix and inclusions. You've got to get big things, 50mm size object from down there getting accelerated. It just doesn't make a lot of sense. And so the way around it is to basically use an extension of the magnetic field lines and use the disk wind itself to this region out here to produce heating and processing of CAIs closer to the region which we actually find them. And so the working of the disk wind is basically accelerate protons, these smack into particles, and that friction actually just causes heating. So if you can do it in the disk further out, you avoid trying to get it out of that gravitational well close to the sun, and you keep the materials close to the position where they can be processed.
In that picture in that right, in order for the material that's accreting in to pull those magnetic field lines, there has to be some ionization. But in the midplane, that's where you don't expect much ionization. Right?
Yeah. So it's about 10 to the minus 8. So most of this activity is occurring on the skin. You're dead right. So most of this is not a whole of disk sort of activity. This is basically a small amount of ionization on the surface and just basically accelerating in that region there. So the skin so this is a fundamental difference in viewpoint as to what we're looking at in terms of a region. We're not looking at a radial region of hot versus cold. We're looking at hot versus cold in the midplane. And so that comes into it in itself. So how hot can we get? Is that a grade or is it? can only go down, can't it? So we have thermal processing in a disk wind. Raquel Solomon and I published that 5 years ago or so now. So we can get up to 2000 Kelvin at 1 AU, just using simple sort of processing and entrainment of these particles in this wind. And so it turns out that the objects will actually float in this wind stream, and you've basically got the fight of buoyancy versus gravitational settling. And that gives you all sorts of dynamics which are really interesting. You get size sorting because you can get lighter materials ejected, heavier particles set back, so the smaller, lighter ones will float away. Particles can grow, so you actually get a history, and that's what's probably happened in some of these. So initial grain radius is about 0.05 centimeters. This gets accelerated up, and then it accretes material, and then it will float back down onto the plane. And they can also be eroded, bladed, and then be ejected as well. So there's all sorts of dynamics that can actually go on in the disk. So as Charlie alluded or addressed initially, the vertical temperature profile of the disk is far more important than the radial one. So we actually get the highest temperatures on the disk surfaces. So that skin can rise to extreme temperatures. How extreme, we're not quite sure yet. I'm still trying to coalesce Raquel into doing some more modeling. And so the real question for us is, do we actually get the higher temperatures close to the sun? Do they stay normal? Is there a regulatory mechanism which is actually going on? And the inner disk and all of this, inner disk is not quite what I mean. The mid-plane disk actually remains relatively cold, and that's still a source of material. So just to show that these just aren't sort of a figment of my imagination, there's recent sort of evidence that these disk winds actually occur. This is the velocity coming out of one of these winds, and this is the radius here. So you have high velocity winds close to the star, close being 10 AU, and then by 20 AU it's sort of dropping down. So there are wind velocities which are quite reasonable for what we're trying to do out to 10 AU. Inside of that, we can't actually see what's going on, because Michael alluded, once you try to get too close to the star, you just don't have the observing capacity to see what's working. So for the solar nebula, I think this is basically a really interesting mechanism for producing the protolith compositions of our solar system. So the disk wind will actually leave behind a residue which is itself devolatilized, and that will be depleted in volatiles as the wind operates. So the inner solar system actually becomes a refractory region. You've still got dust floating around there, it's trying to stay in orbit, and that forms the protoliths for the terrestrial planets. You've still got this outer cooler region as the wind abates. So the wind is actually driving, effectively pushing, devolatilizing and pushing water further out, and will actually generate a snow line for rapid giant planet growth. Can we do the ultimate? Can we actually produce this thermal processing in these rare earth elements? Can we get temperatures sufficiently high? Well, 2000 Kelvin is sufficiently high. So that offers the right environment for actually causing these fractionations. So the interesting thing is that whenever everybody's thought about this, we actually do pick up these ultra-refractory inclusions. You get these ultra-refractory enriched components present in some meteorites. But it's like, well, what are they doing there? And how do they get back associated with this? And so this gives you the right sort of environment, because what you can do is you can evaporate these things under extreme temperature and wind. This condensate component comes off. There's lighter, small particles, either as a bladed, splats onto other particles as it gets further out. You leave behind the ultra-refractory residue because it's bigger, it's heavier, whatever. It still stays behind closer to the midplane. So now you've still got the association of the ultra-refractory components, but you've separated that ultra-refractory component away from the very light stuff. One of the things which is always taken for granted, excellent. Taken for granted is the presence of these iron metal chondrules in some of these meteorites. And and the chondritic meteorites. And these are taken as evidence for planetary collisions. So you formed a planet very early on, you differentiate it, you get the iron nickel metal, then you smack two planetesimals together, and you get droplets of metal coming out, and these separate down and become part of the chondritic assemblage. I think that's not particularly, well, I don't like that model anyway, let's put it that way. So the whole thing is, because you've got density separation, you've got this iron metal coming out here and during this condensation. So during these events, we can actually cook up chondritic material. If you cook it up, you get iron metal coming out. It auto reduces out of anything that looks like a chondritic metal. So you don't actually need to form planetesimals to do this. And that requires a really tight time frame, because some of that metal is as old as the CAIs. Now, it's more likely that it's as old as the CAIs because that metal came into being at the time of the CAI fractionation event. And so you get that metal segregation away from silicates. As soon as you have metal, metal will not react to silicates because of the adverse implications for oxidation. So you've got to oxidize that metal before you can actually get it to react again. Anyway, you get concentration of metal in this little disc, and or the outer disc, and that's going to sink down, it's going to be heavy. And so this forms precursors to the terrestrial planet cores, as well as all the other iron meteorites. So this solves one of the tungsten isotope conundrum. As Yuri said yesterday, you can use hafnium tungsten for dating. And so that's, if you look at this metal, it's just too old. You have not got enough time to form planets, smack them together, and recycle this all into the cosmos. I could talk a lot on oxygen isotopes. I don't really want to, in terms of formation mechanisms. We talked about briefly kinetic fractionation. This is the big fractionation, something I think Yuri showed this, the image of the big variations in oxygen isotopes. This is not a nucleosynthetic effect, this is a chemical effect. It's related to UV photons breaking apart carbon monoxide, and you have basically self-shielding because you run out of photons that will split up the carbon O16 molecule. And so then you get O17 and O18 enrichment deeper in, the oxygen reacts with hydrogen, forms water, and that becomes a reservoir for our solar system. So we end up with our solar composition here, we have nebular water forming out here, and we have carbon monoxide down here because they all fractionate in a complementary, semi-complementary way. We're up here because basically nebular water reacted with some of the silicate dust. That's one of the implications for all this. And the sun appears anomalous to us, but of course it's us who's anomalous. So why am I telling you all this? Well, it's one of these things that drives meteoritics. And so there's all sorts of variability in the oxygen isotopes and CAIs and different compositions of gas. And the disk winds offer that perfect situation where that composition of the gas is going to change depending on how much silicate's in there, how much nebular water is in there, and how much carbon monoxide is in there. So the gas composition just changes with fluctuations in the disk wind. And of course, these just form the precursors for the planets, and so the inner solar system is basically the smoking gun of the disk wind or some other similar process, which is basically driven off the volatiles, and the volatiles are all out in the outer solar system. So last slide. So disk winds are attracted to astrophysics because of the energy considerations and the role in removing angular momentum from a accreting disk. I think it's really attractive to cosmic chemists because it allows you to do thermal processing of the disks. You can get to really high temperatures, which we actually need. And the real key issue is that the products are retained locally. You don't have to start forcing things to try and get them to move around if you can do them in that inner solar system region. There's no point transporting them out because it's wind associated. The wind isn't steady, it's a dynamic thing. It's turbulent, it's driven by Columbia accretion. You can see that from the astrophysical observations. And you're getting cycling of material through the disk. I'll leave it there. Thank you.